Right now, nearly every AI agent on the market is built on a single-player assumption. You prompt, it answers. But this creates a massive bottleneck when you try to deploy that same architecture across an entire company. An enterprise environment doesn't operate like a lone user at a keyboard. It requires a mix of deep, shared collaborative context and strictly segregated individual permissions. When you force a single-player wrapper to serve an organization, the system breaks down. State crosses wires, production secrets bleed across departments, and the context window collapses under the weight of concurrent requests. Personal assistants reach their limit at the organizational level. Serving a whole company requires a system engineered for concurrency from the ground up. Individual productivity tools cannot be duct-taped into enterprise infrastructure. To solve the scale problem, the underlying architecture must change. This brings us to a framework called QNest. It is the first native multiplayer agent harness explicitly designed for startups and large organizations. At its baseline, QM operates as a single headless core. Instead of spinning up isolated apps for every employee, this central nervous system serves the entire organizational chart simultaneously. For the individual employee, the experience feels entirely private. Each person receives a strictly isolated workspace, complete with its own scoped memory, toolchains, and file access. But because it's built on that centralized core, the exact same agent can step out of that private workspace and maintain context inside shared Slack channels and group projects. Enterprise AI relies on this dual state: absolute isolation when working with private data and seamless shared memory when collaborating in the open. This diagram shows QM's three-layer architecture. First, a Postgres database handles session histories and the execution queue. Second, the headless core central router verifies identity and enforces security policies. Finally, data enters the agent loop, where the language model receives its instructions. The language model itself is modular. Engines like Pi, Claude, or Codex easily swap in. Finally, the loop sends execution commands down into heavily bordered nodes. These are the sandboxes, isolated environments where the code actually runs. Decoupling stateful organizational data from the stateless language model prevents cross-user memory contamination. Standard AI coding agents operate in ephemeral environments. Once your session ends, the workspace resets, and all your installed tools vanish. QM solves this by assigning a per-scope sandbox to every specific user or shared room. This is a durable, persistent computer. If you log into a service, configure a test database, or install a specific CLI tool, those states survive permanently between sessions. The agent picks up exactly where it left off. This permanence extends to custom tools, or skills. In QM, skills aren't dumped into a global bucket. They are strictly owned by specific scopes. If an engineer writes a specialized deployment script, they can grant that specific skill to another team's workspace through an explicit, auditable permission. And if a skill proves useful enough for the entire company, pushing it org-wide requires a human administrator to review and approve the promotion. The agent functions within a persistent, fully auditable machine explicitly owned by the user. Moving to the security architecture, QM relies on inherited identity. The agent operates strictly with the credentials and permissions of the human asking it to do the work.
Because identity is inherited, every single command executed by the model is permanently tied to the requesting user and logged for audit. Organizations control access through three security postures. The first is strict, pausing the agent to mandate explicit human approval for every non-trivial tool call. The default posture is auto. An automated classifier acts as a gatekeeper, intercepting and screening external data before it is ever fed into the model. For isolated testing, deployments run in dangerous mode. This gives the agent complete autonomy, disabling content screening and removing pauses between execution steps. But autonomy still has infrastructure-level limits. The absolute failsafe in QM is the pre-declared command policy. It actively blocks actions like recursive directory deletes or destructive SQL drops, completely regardless of the model's intent. Before we look at how this executes in the background, if you are building the next generation of enterprise AI infrastructure, hit subscribe. We dissect systems like this every single week. Autonomy is only safely deployable when it is bounded by infrastructure-level hard stops that operate independently of the model's intent. Most AI workflows are entirely synchronous. The model only processes data when a human is actively typing in a prompt box. QM bypasses this limitation using scoped Crons and file watches, allowing the agent to trigger its own execution loops. You can instruct the agent to wake up on a schedule, study your writing voice, and triage your inbox with drafted replies. Or it can constantly monitor a CI/CD pipeline, automatically pulling logs and investigating failures the moment a build breaks. This background work executes inside the exact same sandbox, respecting the same inherited security policies as your live Slack chats. This means complex organizational work can be securely processed and analyzed while nobody is actively managing the console. Adding asynchronous execution transitions the AI from a reactive conversational assistant into a proactive background worker. The current builder ecosystem focuses heavily on comparing language models. We debate Pi versus OpenCode versus Claude, treating the model as the final product. But inside a system like Quam, the language model is merely a swappable, commoditized compute unit. It is an engine you plug into a socket. The actual, defensible product is the harness wrapped around it. The value lies in the system that manages identity, state persistence, and command policy. As frontier models reach functional parity, the advantage of picking a specific model provider approaches zero. Enterprise value shifts to the durable infrastructure sitting beneath the model. Organizations must stop building workflows around specific models and start building infrastructure that can route any model securely. Ultimately, this architecture results in a synthetic worker that is scoped, permissioned, and audited exactly like a human employee. Because it shares this structural equality with human staff, the traditional organizational chart itself becomes the primary deployment target. Historically, companies bought software and handed it to employees. Now you deploy an autonomous agent node directly alongside the employee, utilizing the same access credentials. If a centralized harness can manage enterprise policy, and the underlying cognitive compute is effectively infinite, what does the physical shape of a company look like in 5 years? I'm from Synthic Labs, and our mission is moving these concepts from research papers to working prototypes. Thanks for watching.